Hello, friends. This is me again. Welcome you to my YouTube channel called Viruses. Today, I'll be talking to us on how the basic properties of viruses lead to diseases. By this time, you know some of the basic properties of viruses. They are microscopically minute, cannot be seen with the naked eye. Metabolically inert, they don't replicate on their own because they don't have a functional ribosome. They are obligatory intracellular infectious entities, obligatory. They have to enter into a cell before they can set up an infection. They contain only one type of nucleic acid, which we refer to as genome, which can either be DNA or RNA, never both. They are not capable of independent replication. They can neither synthesize their own energy or protein because they don't have the mitochondria or the ribosome. They replicate only on living cells because of this property of having only one type of nucleic acid. So what are some viral diseases? I've given us the general basic properties. Viruses cause disease, starting from even the common cold, to seasonal flu, to even the most serious illness such as AIDS, acquired immunodeficiency syndrome, dengue virus, measles, Ebola disease, COVID-19, and yellow fever. On top of this picture is a patient will cope with a common cold, like flu, whereas down below is a patient, an HIV patient already showing some signs of Kaposi sarcoma. How do they induce diseases? How do viruses induce diseases? All viruses infect cells. They induce diseases by infecting the cells. They redirect the whole cellular machinery for their own benefit. And so therefore, the knowledge of the biology and structure of these viruses help us to better understand the disease they cause and how to prevent and treat them. Viral infection actually starts with replication of the virus in the whole cell. Start with the replication of the virus in the whole cell. They have to enter. The virus has to enter in this whole cell, recognizing a receptor at the surface of the whole cell. At the surface of the whole cell. Once they recognize that cell and attach, they begin to reproduce their genomes. They begin to reproduce their genome in the cytoplasm of the whole cell. During this process, they generate abundant copies of their nucleic acid, which we are seeing in the picture on the right. They generate abundant copies of their nucleic acid to continue to spread, and they continue to spread from cell to cell through this process. And what follows then? At this point, the cell is dead, and the virus had to be assembled and had to get out of the dead cell in order to infect another living cell. That is the process we call budding. They bud out of the infected cells. During this process, what happens? The host provides all the resources the virus needs. Other components needed for making of the protein are also as directed by the virus. This is the word I've been using often and often. They hijack all the macromolecules, all the organelles of their host for their own benefit. So this eventually leads to pathogenesis. What is pathogenesis? This is the induction of the disease. The process that eventually leads to the induction of the disease in the host. This is an integrated result of many complex factors. Pathogenesis is an integrated result of many complex factors which are unique to the particular virus, unique to the species, and also unique to the individual host. That's why we see the different clinical manifestations of diseases. So the interplay of these factors, therefore, determine the nature of the infection. Is it going to be chronic? Is it acute? Is it severe? Is it latent? It's the interplay of these factors that eventually determine the nature. Is it subclinical? Is it apparent? And so on. Is it latent? These are all the things, this interplay that determines, and this is a very good one. This is what I'm talking about. This is showing the interplay of host and viral factors. Under the host factor are the age. Some viral diseases are age-related. Some are age-related. Some determined by the immune status. Is the host having an antibody? Did they have a prior exposure? Is it vaccinated? Some viral diseases are common to women more than men and vice versa. And of course, some genetics. The genetic makeup of the host determine a lot. Of course, the geographical location of the patient, of the viruses. Some viruses survive in the tropic more than they survive in the temperate region, and vice versa. And of course, the economic social status. What is the level of surveillance in that country? What is the level of what is the socioeconomic importance? How many hospitals to the population? How many doctors to the patient, to the population? These are all the things. As far as the viral factors, one important thing there is the virulence. How virulent? How pathogenic? How serious is the virus? What is the portal of entry? How do they gain access? How do they gain access to the body, to the host? How do they gain access to and what is the mode of transmission? Is it through fecal-oral, through injection of contaminated food, or is it through sneezing, coughing, respiratory? Is it through sexual intercourse? A virus that is supposed to be transmitted fecal-oral, if it breathes in through the respiratory tract, it may not set off an infection. Then the dosage of the virus the patient is actually receiving, very, very important. And of course, the strain of the virus. You see a very, very virulent virus like Ebola, or again the stability of the virus. Is the virus stable under normal condition, under adverse environmental condition? One good thing we need to know about viruses is that there are two groups of viruses. We have the envelope viruses and the non-envelope viruses. Envelope viruses are less stable. They are easily destroyed by chemicals, by disinfectant, and so on and so forth. Whereas the non-envelope viruses, they are really very stable. They are really stable. They are difficult at times to control. How do they damage cells? How do viruses damage cells? Some of them damage cells by direct killing. By direct killing or by direct induction, by direct inhibition of the macromolecules. That one we know already. Or by the loss of function, paralysis as we see in polio, or hemorrhages as we see from that picture that is being represented in this slide. Hemorrhages, blood coming from every part of the body, from the nose, from the mouth, from the eye. Hemorrhages, leakage of blood from blood cells from all parts of the body, causing hemorrhages. Then some can be by overstimulation of infected cells. This is very, very common with gastrointestinal viruses, like the rotaviruses. They cause, which eventually lead to isotonic diarrhea. Those are all the way. How again do they cause damages? Another interesting part is the integration. Some viruses like HIV, they have the capability of integrating their own genome into the whole cell, into the whole genome, leading to what we call as proviruses. That is why for HIV, once a patient is infected with HIV and a provirus is formed, because antibody cannot reach it, antiviral drug cannot reach it, so that patient becomes infected forever. Another integration is with the oncogenic viruses, for the tumor viruses, where the virus integrate to form oncogenes. They form oncogenes. Another interesting thing is when the host immune system, instead of playing a defensive role, is playing an offensive role here. A very good example here is the measles. What the rashes we see in measles is not the direct effect of the virus. It's not the direct killing of the virus, but as a result of immunological attack on the whole cell by the measles virus. Again, a mutation, as we see in the host genome in COVID-19, is also. So all I've just been telling us about what happens at the cell level. But let's see now what happens at the patient level. Pathogenesis, disease is characterized by incubation period. The incubation period is the time between the initial infection and the time when the first clinical symptoms begin to appear. And then this is immediately followed by the prodromal period, which can also refer to as the non-specific. For those signs we see are not particularly specific for that disease. A good example is where there's cold, that patient is feeling cold, his body temperature rises, and so on and so forth. You cannot tie that particular symptom to that particular virus. Then, if the patient is non-immune, if it has no previous exposure or immune antibody against that virus, that non-specific symptom will now translate to specific symptom. What do we see now? Those viruses produce specific symptoms. A very good example is the paralysis in polio, and the cough and the damage to lungs we see in COVID-19, and the abnormal loss of weight and hemorrhages in Ebola and HIV. Infection, at this point, depending on one of those host factors, the patient may recover. But most of the time, the patient may not recover, and the disease may transit to chronic, latent, and persistent form of the disease. Infection may become chronic or latent. Chronic. That is where the virus is there, but it's not manifesting the clinical symptom, as we shall see in the acute phases. Viral clearance from or persistence. The majority of viral infections are cleared from their host. Certain viruses may cause persistent infection. There are actually two types of chronic persistent infection. The true latency. A very good example here is the shingles versus chickenpox. What actually happened? The virus, instead of being cleared from the host, finds a latent site. We refer to them as latent site. They find a latent site where they hibernate, where they are there, but they are not replicating. So because they are not replicating, they are persistent in that place, but they can be reactivated. Adverse conditions can reactivate those viruses. One of the things that can reactivate those viruses is stress, overworking, insomnia. You are not sleeping well. For our women, during the menstrual period, those are the factors that are actually reactivate some of those latent viruses. And for those that are persistent, those that exhibit persistent manifestation, the virus replicates continuously. They continue to replicate continuously in the body of their host for a very long time at a very low level. A very good example is HIV. That's why because they are replicating at a very low level. At a very low level, the incubation period can be as long as 10 to 15 years. That is why we see in HIV, before transition to eventual immunodeficiency syndrome, we see the long incubation period. The disease, the virus is persistent, and they are not being neutralized. Even though they are in the body, but they are not being neutralized by the antibody in the host. So they remain persistent. In the host. So I think that is all my slides for today. I hope you have enjoyed my lecture. I want you to please subscribe, share, and like. So I expect to see you again in my next slide, in my next video. Please subscribe, share it with your friends, share it with your colleagues, students, share it among yourself, clinicians, share it among yourself. I know there are some information you are getting from this video. So therefore, I want to see you more in my video. Thank you very much for your attention. I'll be seeing you in my next video. Thank you and good night.